Hello everyone. In this video we talk about Taylor series, which, to give you essence, is the highlight of this chapter. But before we talk about Taylor series, let's review the two topics that we discussed so far within this chapter. First, a Taylor polynomial centered at A. If you recall from section 11.1, a Taylor polynomial centered at A is f of A plus f prime of A times x minus A plus f double prime of A divided by 2 factorial times x minus A squared, and I can keep on this pattern going. And in sum notation, we write that as the sum starting at 0, ending at n being whatever degree I want that Taylor polynomial to be, of the coefficient, the kth derivative of f, evaluated at where I'm centering my approximation at, divided by k factorial times x minus a to the kth power. And the reason why we talked about them before was, remember that we discussed that the power of a Taylor polynomial is that they approximate f of x by matching to 0, first, second, up to the nth derivative when I evaluate that at a. And that was our first goal of a Taylor polynomial, is how can I approximate the function using the nth order Taylor polynomial. The second main topic we talked about was a power series, which essentially extends and makes it more general, our Taylor polynomial, where instead of the specific coefficient that we written in pink, we now have just in general the coefficient c of k, and this keeps going from 0 to infinity. Keep in mind that they converge at a particular interval determined by this quantity. And if you recall, this essentially forms an interval because I can always rewrite absolute value of x minus a less than r as negative r less than x minus a, which is less than r. And if I add both sides by a, I can rewrite that as a minus r less than x less than a plus r. And if you recall, this forms an interval. Now, I don't make any assumptions about the endpoints. Remember that we have to plug the endpoints in and check if we still have convergence to determine whether or not we can conclude that. Well, the idea of a Taylor series is very simple in the sense, scrolled up a little bit, in the sense that I am combining these two concepts together. I'm essentially taking a power series, and now with that power series, I am saying, let the coefficients in C of k be the coefficients that we saw when we were doing a Taylor polynomial. So in essence, a Taylor series centered at A is a power series with the same coefficients as a Taylor polynomial. Another way that you could think of a Taylor series, it is a Taylor polynomial where the degree of the polynomial n is going to infinity. Because if you recall from our original formula, that degree n goes at the top of my sum. The only main change I did from my formula for a Taylor series to my formula for a Taylor polynomial was, instead of writing n at the top of my series, I wrote infinity. That's all I did. Now, before we go through and tackle some examples, there is one special Taylor series that I will mention, and that is the case when I decided to center it at 0. And this has occurred a lot, and so because of that, we've actually given this Taylor series centered at 0 a special name, Claude Maclaurin series. So in that sense, in any calculus textbooks, if you see the term Maclaurin series, all that is a Taylor series centered at 0. And a lot of calculus textbooks are not going to say, find a Taylor series centered at 0. They're going to be lazy and say, let's take the Maclaurin series of that. And because they're the most common form of a Taylor series, we give it a special name called the Maclaurin series. But there's our idea. Let's figure out how we can form a Maclaurin series for a function. And how can we determine its radius of convergence? Well, the first thing that we need to do is to find the coefficients. And to find those coefficients, fk, f the kth derivative of f at a, I say that is the same methodology that we did way back in session 11.1, when we tried to find the coefficients for a Taylor polynomial. So that means I'm going to take the derivative of f of x multiple times and then evaluate it at a center. And because I'm told that I want to find the Maclaurin series, I am told that the center is 0. So let's do that. Since f of x is e to the x, the derivatives are boring in a sense, because this is the one function where the derivative is just itself. No matter how many times I take its derivative, I'm still going to get e to the x. Now, and then if I plug in 0, that's e to the 0, that's an exponent, so that means I'm going to get 1. Which means that all the coefficients will just give me 1. And so that means my Taylor series, or Maclaurin series, will be the following. So thus, the Maclaurin series is the following. First, my function f evaluated at the center plus my first derivative evaluated at the center over 1 factorial times x minus 0, which is the center, plus the second derivative over 2 factorial x minus 0 squared, and so on. But we can simplify this a lot in the sense, because I know that I don't care how far I go, I'm always going to get 1 here. And because my center is 0, I can just replace it with x, I can replace it with x squared, and so on and so forth. So now I have 1 plus x squared over 2 factorial, and then if I kept going, I'll have x cubed over 3 factorial, x to the 4th over 4 factorial, and so on. And it may be hard to relate x and 1 to the rest of the series, But always keep in mind, I do have 1 factorial in there. And I could rewrite 1 as x to the 0 power. Keep in mind that we have a special scenario that 0 factorial equals 1. So now I have an underlying pattern for the entire series. So I can now write that in series notation as the sum going from k goes to 0 to infinity of x to the k power divided by k factorial. And yes, my friends, give me the Maclaurin series for e to the x for that guy. But that's just a good old power series. So I want to know when that series converges. And so let's figure that out. Because I see a factorial in the series notation, I'm going to try to ratio test. Remember, a of k is just s of k over k factorial. A of k plus 1 just means that wherever I saw a k originally, I'm going to replace with k plus 1. And now by the ratio test, L equals the limit k goes to infinity a of k plus 1 over a of k, or copy down the next term over times the reciprocal of the current term. Alright, and now we can do some cancellation. That simplifies down to k plus 1, and that simplifies to x. So now inside the absolute value, I have absolute value of x over k plus 1. I'm going to use my property of absolute value that says it is the absolute value for x times 1 over k plus 1. So I have absolute value for x times the limit as k goes to infinity of 1 over k plus 1. But knowing from what we learned in Cal 1, we know that limit better give me 0, which means the whole thing is 0, and that's definitely less than 1 no matter what. And so this is brand new for us. I don't have an absolute value for x anymore, and I use that to form my radius of convergence and my interval convergence. So here's what that means. Because I do not have an x popping in here anymore, so I'll write that down. Because no absolute value for x is here, and remember in power series we use that to form our interval of convergence. What that means is all values of x are valid. And what does that mean? That means it does not matter within my Maclaurin series what value for x I plug in, I will always get a convergent series, no ifs, ands, or buts. Thus, we can write that conclusion that we conclude by the ratio test that the series converges for all x, which means my radius of convergence would be infinity. And the reason why I'm concluding infinity is because since all values for x are fair game to make the series converge, then that means I don't need to form a cap for my radius of convergence. So my radius of convergence can be infinity. And as a side note, that means the interval of convergence is every real number that I can think of. So negative infinity to positive infinity. Alright, so let's go ahead and get the cosine first, and let's start with sine next. And the reason why I'm going to do cosine later is to recall a property from section 11.2. Well, let's start finding the Maclaurin series for sine. Well, we're going to do the same methodology that we did with example 1, where we're going to find f of x, which is just sine. And because we learned from tensicity that every fourth derivative I get back sine, as soon as I take the first, second, third, and fourth derivative, I should know where I'm going it to. Or I'm just going to take up to the third derivative. Since at the fourth derivative, I'll just get back to sine. So first derivative gives me cosine. Second derivative gives me negative sine of x. Third derivative gives me negative cosine of x. And now let's plug that in at the center. And because we have a Maclaurin series, that means a will equal 0. So f of 0, which means I'm plugging in sine of 0, which just gives me 0. First derivative of 0, well, that's just cosine evaluated at 0, which gives me 1. Second derivative at 0, that gives me 0 again. And then the third derivative at 0, that gives me negative 1. So that means the Maclaurin series will be f evaluated at 0 plus the first derivative evaluated at 0 over 1 factorial x minus the center plus the second derivative evaluated at 0 over 2 factorial x minus 0 squared, and then the third derivative of 0, 3 factorial x minus 0 cubed, and so on. But from our work, we know that gives me 0, that gives me 1, this is again 0, that gives me negative 1. So after simplifying, what I have is 1 over 1 factorial times x, negative 1, so minus 1 over 3 factorial x cubed. And because the fifth derivative means I'm back at the first derivative, because remember, fourth derivative of sine, I get back to sine, so that means the fifth derivative is equivalent to the first derivative, which is cosine, which means I expect that if I kept going to the fifth derivative, that will be my new coefficient. Sixth derivative, that's equivalent to the second derivative, I get 0 again. Seventh derivative, that's equivalent to the third derivative, so I better get a negative 1. And so that is what I expect to be my next coefficient. And if I keep repeating the pattern, this is what I should expect to see. Now, let's dissect what's going on. So this is my series that is forming, and I want to write this in a condensed sum formation. Let's figure out how we can do that. So, if I'm starting off at 0, And then this means this is when k equals 0. And let's check what's going on. I still have an x popping in, and I still have a 1 factorial in there. This is my k equals 1, this is my k equals 2, this is my k equals 3, and so on. So one pattern that I'm noticing is the exponent in each of the powers of x are odd. Not only that, that power is corresponding to what's inside the factorial. Because of that, that means that my power in my factorial has to be my general formula for an odd number. And if you recall from way back in trig integrals when we talked about odd, I can always write an odd number in the form 2k plus 1. So because of that, two things that are going to be in my Taylor series is 2k plus 1 factorial. To correspond that in my denominator, I better have an odd number taking a factorial of. And in the exponent, I'm also going to have not 2n plus 1, 2k plus 1. To correspond to the fact that I better have an odd power in my exponent. But I'm not done necessarily, because I note that a k equals 1, I have a negative sign. A k equals 2, I don't. K equals 3, I do. 4, I do. 5, I do. 4, I do not. 5, I do. Which means that 1, 3, 5, and all of the odd terms, I better have a negative sign. And because it is my odd terms that better have a negative sign, it's going to be negative 1 to the kth power to correspond to that. Thus, my Maclaurin series, Fourier Sky, is the sum from k equals 0 to infinity of negative 1 to the kth power as to 2 to the kth power plus 1 divided by 2k plus 1 factorial. And now let's get back to example 2. And now let's check and see why I decided to wait until we did example 3. So to find the Maclaurin series, we could do the previous method that we've done before. But here's going to be my observation. Recall that if I take the derivative of sine of x, let's make that black, I get back cosine. And why did I make that observation? Because in section 11.2, we talked about that for a power series, we can take a derivative of a power series term by term. And so thus, because of that observation, I can quickly form the Maclaurin series of cosine as follows. I know the Taylor series for sine. So instead of doing the work I did previously and doing that long, tedious work to find the Maclaurin series for cosine, what I'm going to do is I'm going to take my Maclaurin series for sine that I found previously, and then I'm going to use my property of power series that says derivative of a power series is the exact same as moving the derivative inside the power series and taking the derivative term by term. So negative 1 to the kth power, x to the 2k plus 1 over 2k plus 1 factorial. And this makes it work a lot easier. Well, the only value for x I see is the x to 2k plus 1. So that means by power rule, we get negative 1 to the kth power. Derivative of x to the 2k plus 1 by power rule will be 2k plus 1. And then x to the 2k power, since I have to subtract 1 from my old exponent to give me my new exponent, divided by 2k plus 1 factorial. Note that I can simplify it a lot further, because I can rewrite 2k plus 1 factorial as the following. 2k as 2k plus 1 times 2k factorial. And now I have a 2k plus 1 on the numerator and a 2k plus 1 in the denominator, which means they go away, which now gives me my Maclaurin series for cosine as negative 1 to the kth power x to the 2k over 2k factorial. And that, my friends, gives me the Maclaurin series for cosine using properties that we discussed before. And note, if I wanted to do this in reverse, I could. I could have found the Maclaurin series for cosine in the tedious way, and then I could say, okay, well, for example 3, the antiderivative of cosine of x is sine of x, and I could have done a property that says taking the integral of the power series is the same as taking the integral term by term. I could have done it that way. Well, now let's use Taylor series with some other properties of power series that we dealt with before. And let's find the Maclaurin series for the function f of x equals s times cosine of x. Well, I know that the Maclaurin series for cosine from the previous example that we worked on is the sum k equals 0 to infinity of negative 1 to the kth power s to the 2k power times 2k factorial. And I can now use my property that we talked about before in section 11.2 that says if I have x raised by some power outside of the power series, I can move that inside the power series and combine those x's as I would expect to give me, in the end, the sum from k equals 0 to infinity of negative 1 to the kth power times x. And now, since I moved that x inside, my exponent is now 2k plus 1. And then 2k factorial. And there is our Maclaurin series from that slight modification. And the reason why I want to mention example 4 is while you could do the long, tedious way that we talked about before, don't forget our properties of power series from 11.2. And I'll write down the general form here for a reference of what property I use. Property was, if I have x raised to the n power in a power series, I can essentially say move that power inside and give me the new power series ck of x, but now raised to the n plus k power. Alright, and now let's change it up. Let's find the Taylor series for sine, but now I said center at pi over 3. And how's that going to change our work? Well, the original setup is still going to be the same. So I'm going to write sine, I'm going to write the first derivative, I'm going to write the second derivative, I'm going to write the third derivative. Negative cosine of x, negative sine of x. And then now, instead of plugging in 0, I am now plugging in my brand new center, which is pi over 3. Which means I'm going to evaluate sine at pi over 3, which is root 3 over 2. First derivative at pi over 3, that's going to be cosine of pi over 3, which is 1/2. Second derivative at pi over 3, that's negative sine at pi over 3, so negative root 3 over 2, and then the third derivative at pi over 3, that's negative cosine at pi over 3, so negative 1/2. And I'm not going any further because we know that our fourth derivative just gives me back the sine. So let's write down the Taylor series in explicit form. The Taylor series is the following. I have f evaluated at pi over 3, then the first derivative at pi over 3 over 1 factorial. But now instead of 0, I have minus pi over 3 plus the second derivative at pi over 3 over 2 factorial. That's minus pi over 3 squared plus third derivative of pi over 3 factorial x minus pi over 3 cubed. And then I'm not going any further because the pattern just keeps going. Alright, and from our work previously, we know that f of pi over 3 is root 3 over 2 plus 1/2 over 1 factorial x minus pi over 3. Second derivative, I get to negative root 3 over 2. So minus root 3 over 2 divided by 2 factorial times x minus pi over 3 that squared. Let's make that 2 a little bit pretty. Plus third derivative, which is just negative 1/2 3 factorial x minus pi over 3 cubed, and then the pattern keeps on going. So as of right now, I don't see an explicit pattern to write in a generic form. But one thing I am noticing is some of the coefficients are root 3 over 2. Some of them are 1/2. And so because of that, if I don't see a pattern immediately, what my game plan is I'm going to match it with the coefficients. And then I'm going to regroup the series based off of those coefficients. So that means I'm going to group together all the coefficients with root 3 over 2. So root 3 over 2. I'm going to now group this one in pink. And because I have a fraction in the numerator, I'm going to rewrite that as 2 times 2 factorial x minus pi over 3 squared. And I expect when I get to the fourth derivative, remember, fourth derivative of sine is sine again. So my coefficient will be root 3 over 2. So it would be root 3 over 2 times 4 factorial x minus pi over 3 to the 4th power. And then 6 factorial, 6th derivative would be negative sign again. So negative root 3 over 2 times 6 factorial x minus pi over 3 to the 6th power, and so on. And I do the exact same work with the 1/2 coefficients. 1/2 times 1 factorial x minus pi over 3 minus 1 over 2 times 3 factorial x minus pi over 3 to the cubed power. And then if I go back to 5, because that'll be the next one that has the 5 fifth derivative is the same as cosine. So I have 1 over 2 times 5 factorial x minus pi over 3 to the 5th power, and so on. Now, with this rearrangement, I now see a pattern that's going on. In the one in pink, the factorials that are occurring, where, remember, 0 factorial was 1, I see that I have 3 halves, an even base in my factorial, and an even power in the x minus pi over 3 portion. And again, I see in blue an odd base in the factorial and an odd power in my x minus pi over 3. Which means if I want to write this out in explicit series form, for the first series, it would be the sum from k equals 0 to infinity. Now because this is now k equals 1, k equals 2, k equals 1, k equals 3, have negative 1 to the kth power, root 3 times 2 times an even base times an even power with that, plus another series n 0 to infinity of negative 1 to the kth power again to represent that I'm alternating. But now 2 times odd base in the factorial and odd power. Oh, Chris is averted. Ah, crap. There we go. and odd power with dx minus pi over 3. And this, my friends, is one epic problem to find a Taylor series. Now, for the next example that I'm going to do, I'm actually going to leave yes as a bonus problem. If you look at the bottom, you should know what the actual series will look like. But I'm going to leave this for y'all as an exercise. To find the Maclaurin series for that series. So, you're going to have fun with that. I'm not going to lie to y'all. But what I want to get to now is something that seems weird because we've been talking about so far, well, we talked about Taylor series of a function. Why on God's green earth am I talking about when does a Taylor series equals to its function? Well, one thing that I want to recall, throughout the examples that I've done, I have never written e to the x equal to its Maclaurin series, nor did I do it for sine, nor did I do it for cosine. And the reason why is I can't quite do that yet. So, what we have shown is that if f can be represented as a power series, then f is equal to the sum of it. But what makes it harder is that there are some tricky functions where they are not equal to their Taylor series. And one example that I gave was this weird guy, f of x, which is e to the negative x squared for all positive numbers, and then 0 everywhere else. And I'll go ahead and, I'm not going to show why f of x is not equal to its Taylor series, but I'll quickly explain it. It's when you find the coefficients you will always get 0. And that makes it weird in that sense because you're telling me that if I assume that all Taylor series are equal to its function, you're telling me that f of x, this f of x that I define equals 0, no ifs, ands, or buts. Well, that's not true. That's definitely not 0 everywhere. And so, because of weird examples like that, we have to be very careful about when can we say a Taylor series equals to its function. So the next part of this section is, under what circumstance can I make the following claim that the function f of x equals to its corresponding Taylor series? And here's going to be my way of tackling it. Is with any convergent series, remember that a convergent series, by definition, and this is the definition that we had a long time ago, is a limit of all of it, of a sequence of partial sums. And so what does a sequence of partial sum looks like for a Taylor series? Well, it's just the nth order Taylor polynomial. Because if I write out the partial sum of a Taylor series, I just get back a Taylor polynomial. And so what that means is If I want to say that f of x is the sum of its Taylor series, I must have that f of x must equal to the limit of its Taylor polynomials as n goes to infinity. And now you might be saying, now Scott, why on God's green earth does that help me? That just gives me some jargon. Well, here's why that helps me. So recall from section 11.1 that we talked about the remainder of a Taylor polynomial as the function that I have in the beginning minus its approximation. And we also recall that one of the key things from Taylor's theorem that we have is that I can always rewrite f of x as its approximation plus its remainder. No matter what, I can always rewrite it in that form, which means I could figure out what makes one true. So if I take the limit as n goes to infinity of f of x, well, by what we have in box, that's the same as taking the limit as n goes to infinity of the nth order Taylor polynomial plus the nth remainder. Okay, and one property of limits that we have is that limit of a sum of two functions is the exact same as taking the limit of each component. So p of n of x plus the limit as n goes to infinity of the remainder. Now, one thing to keep in mind, I'm taking the limit with respect to n. F is just a function of x, and it could be arbitrary for what I want. So with respect to that limit, f of x is just a constant. So I essentially have f of x equal to the limit of p of n times the limit of the remainder. And what I want to show if this series is true is f of x equals to the limit of the Taylor polynomial. Well, right now I have just a extra part of that, and that is the limit as n goes to infinity of the remainder, which means if I can make that go away, I have the equation in 1. So if I know that the limit as n goes to infinity of the remainder equals 0, then I can rewrite this as f of x equals the limit as n goes to infinity of the nth order Taylor polynomial plus the limit of the remainder. Because I am now saying I already know a priori that that limit is 0, I get the condition that I want, which is the limit as n goes to infinity of the nth order Taylor polynomial. Which implies that in order for me to say that a function is equal to its Taylor series, I need to have the remainder go to 0. And that is what's summarized in that Ness theorem. It is saying that for a function to be equal to its Taylor series, I must have the limit as n goes to infinity of its remainder to equal 0. And recall that Taylor's theorem gives us this expression for the remainder, where c is some value in between the center and x. So now we have our condition to figure out when a Taylor series is equal to the function. And for that, let's now go ahead and show that the Maclaurin series that we found for e to the x is actually e to the x. And I'll show how we can actually prove that. So let's go ahead and explicitly write down the remainder for e to the x. It's the n plus 1 derivative evaluated at c, n plus 1 factorial, s raised to the n plus 1. But remember that my function f is e to the x. Derivative of e to the x is just itself. Evaluated at c just gives me e to the c. Evaluated at n plus 1 factorial, that's 2 n plus 1. Where that value c is between, in this case my center is 0. So c is just somewhere between 0 and x. So I now have an expression for the remainder. Now I need to take the limit as n goes to infinity of the nth remainder of evaluated at x. That's the limit as n goes to infinity. E to the c power over n plus 1 factorial times x to the n plus 1. Taking a limit with respect to n. So that means e to the c power is just a constant with respect to the limit. So that means e to the c times the limit as n goes to infinity, x to the n plus 1 over n plus 1 factorial. And I claim that that limit goes to 0. Now let's quickly explain why. My numerator is x to the n plus 1. No matter what number I plug in, for x, if I plug in 1, I just have 1. If I plug in 2, I have 2 raised to the n plus 1 power. It doesn't matter what value for x I plug in. This is going to be a case where I have an exponential function where the base is fixed. But, something's popping up. I don't want a sticky note. Sorry about that, y'all. And I do that for all of them. So because the remainder is 0, by my theorem, that is telling me that I can now boldly claim that e to the x equals Taylor series. So therefore, we can now say that the sum of x to the k power, or is Taylor series, we can now boldly say that that equals to e to the x, because now I know that the remainder goes to 0. Let's try that again with another example where we're trying to find that the Maclaurin series for cosine converges, that's a typo, for x inside any real number. And we're going to play that exact same game. But here is going to be a little bit harder because we're going to have the same expression for the remainder. N plus 1 factorial x n plus 1. And here's why it's a little bit trickier. The n plus 1 derivative at c Well, if n is odd, then that means n plus 1 will be even. So I'm going to have plus or minus cosine of c if n is odd, plus or minus sine of c when n is even. Which means we can't do the same trick that we saw in example 7. That means we're going to have to get around that issue. And here's how I'm thinking of us getting around that issue. We're going to use some tools that we've seen before. So to circumvent this issue, what I'm thinking of to solve this problem is I want to use a combination of our theorem from section 11.1, which tells us how we can estimate the remainder, and we're also going to use squeeze theorem. And here's the reason why I'm thinking of using squeeze theorem. If I write down my general form for estimating the remainder, well, absolute value, there's no way an absolute value number can be negative. And the only way that I get 0 is if I'm taking the absolute value for 0. So 0 is less than or equal to the remainder, but, it scrolled up. But that is less than or equal to, call for the estimating the remainder theorem, that all I'm doing is moving around with the absolute value. And because my n plus 1 derivative of f at c is either sine or cosine, I can always bound this guy as being a number that is less than 1. Which means, in the end, this is bounded by the absolute value of x to the n plus 1 over n plus 1 factorial. And here's again what that means. I'm going to plug in, oh crap, it's going everywhere now. There we go. Going to be the limit as n goes to infinity of 0 less than or equal to the limit as n goes to infinity of the absolute value of the remainder less than or equal to the limit as n goes to infinity of x to the n plus 1 power over n plus 1 factorial. And now let's evaluate that guy. Well, limit of a constant is just a constant. And this is going to equal 0 because no matter what value for x I plug in by growth rates, this will always grow significantly smaller than n plus 1 factorial. Which means I can conclude by squeeze theorem, therefore, and I'm going to use the therefore symbol, which is just a triforce, to note that the remainder is going to 0. Which therefore means I can make now the solid conclusion that cosine of x equals is Taylor series, is Maclaurin series, and I don't have to use the weird thing is, yeah, here's the Taylor series, but I don't know if it's equal or not. Now I boldly know it's equal because I showed that the limit of the remainder equals 0. And here's a note that I want to make. So if you want a table for a common Maclaurin series, I provide those at the end of the lecture notes. And these are some of the most common ones that we'll typically see. Alright, and that concludes the end of this video. Make sure that you like, comment, subscribe, smash that notification bell, and smash that like button. Alright, see ya.